the next thing we're going to do with inverse trig functions is we're going to create algebraic expressions. When we do that, oftentimes we're going to be asked to rewrite some information we're given that involves trig or inverse trig functions in terms of kind of anything other than trig functions or inverse trig functions. So one of the things that we need to first remember that inverse trig functions represent rotations, and I'm going to add to that and say that trig functions are ratios. Okay? Sine is opposite over hypotenuse, cosine adjacent over hypotenuse, and tangent, of course, opposite over adjacent. We have that SOHCAHTOA to help us remember. And right triangles can almost always be drawn to help when we're dealing with trig functions. So let's look at here at example 1. I have sine of arc cosine of x, and I have to rewrite that as some kind of an expression that involves x, but does not involve any kind of trigonometric functions. So the first thing I'm going to recognize is that arc cosine of x, that's just some rotation. It's telling me that the adjacent divided by the hypotenuse of some unknown rotation that I have decided to call theta is equal to x, or if I want to, I can say that's a fraction of x over 1, so that does indeed give me my adjacent and my hypotenuse. So I'm trying to find the sine of that unknown theta. Well, because they're trig functions and because I have a side ratio, I'm going to go ahead and draw a right triangle. And I'm going to assume x is positive, so I'm going to assume I'm in the first quadrant. And I'm going to go ahead and say some theta, some rotation, has an adjacent of x and a hypotenuse of 1. Well, if I want to find the sine of this rotation, I'm going to have that opposite side. Well, this is what I was able to come up with what I'm given. Now I'm going to use some math to help me find some more information about this triangle. I'm going to go ahead and use Pythagorean's theorem to figure out that missing opposite side. So I'm going to say 1 squared equals x squared plus some unknown side squared. Well, I can get a squared by itself by saying 1 minus x squared equals a squared, which tells me this side here must be the square root of 1 minus x squared. Well, then couldn't I figure out sine? If sine is opposite over hypotenuse, I have an opposite and a hypotenuse. And it's 1 minus square root of 1 minus x squared all over 1, which is just the square root of 1 minus x squared. Looking at example 2. So notice because I was just trying to find in the end a side ratio anyway, I never really needed to know what that rotation was, as long as I had enough information to come up with a side ratio. I'm going to do the same thing in example 2. So I'm going to recognize that whenever I have an inverse trig function, it means a rotation. So let's say this time I call my rotation, how about I call it alpha? So I'm saying, since I have sine, that the opposite over hypotenuse of some rotation that I've decided to name alpha is x, or x over 1 if I want to write it as a ratio. Well, now aren't I trying to find out the cotangent value of that alpha? And isn't cotangent just adjacent over opposite? I have the opposite, I don't have the adjacent. But if I have two side lengths, I can draw a right triangle and use Pythagorean's theorem to find the missing one. So here's my triangle, here's my unknown alpha that has an opposite of x and an adjacent of 1. I can now take what I was given and I can fill the rest in using Pythagorean's theorem. So 1 squared plus x squared equals some c squared. Well, that means c equals the square root of 1 plus x squared. And now I have an adjacent. And, oh, I'm sorry, this is incorrect. Let me erase this. I was given an opposite over hypotenuse, not an opposite over adjacent. So this is what I knew. I'm really sorry about that. And then from here, I can now find my opposite and adjacent. This was my hypotenuse, and I put it on for my adjacent side. But going through the same thought process, I'll have 1 squared equals x squared plus some unknown, the bottom, the base. So then I can say 1 minus x squared equals b squared, and I can go ahead and label this adjacent side as the square root of 1 minus x squared, and then that allows me to now name my cotangent. Cotangent of alpha is going to be adjacent, which I just found to be 1 minus x squared, all under the radical, over my opposite side, which I know to be x. And let's look at one more example like this. And so the final example, I'm going to go through somewhat of the same process. First thing I'm going to do is recognize that this is an inverse trig function, therefore it's some rotation. Maybe I'll call it theta again. So I know that since it's tangent, the opposite over adjacent of some rotation, which I am choosing to call theta, is equal to x over 2. So I want to find the secant of that theta. I want to find the hypotenuse over adjacent of that. Well, let's look at a triangle, because once again, if I'm given trig functions and I'm given a ratio, I can draw a triangle and use Pythagorean's theorem to find my missing side. So here's my unknown theta that has an opposite over adjacent of x over 2. I can now fill in what I'm missing by using Pythagorean's theorem. So Pythagorean's theorem is a squared plus b squared equals my c squared. So this is going to be the square root of x squared plus 4. And therefore my hypotenuse over my adjacent is square root of x squared plus 4 all over my adjacent, which was 2. So once again, real quick to end this video, just to summarize, make sure that you're recognizing that inverse functions are rotations, and if you're given an unknown rotation with a side ratio, you can go ahead and create a right triangle and use Pythagorean's theorem to fill in with your missing, and then you can find whatever new ratio you're being asked to find depending on the trig function you're given.